I też można też nie krzyczeć.
Patryk Mach from Jagiellonian University, and he's our common visitor, so most of us know him. And he'll talk about calculation this.
Okay, thank you very much. Thank you very much for the invitation. It's always a pleasure to be here. Well, I wanted initially to talk about what we are doing right now about Vlasov systems in Krakow. Professor Piechocki convinced me that because I talked about that in Łódź, and probably many of you have heard those results already in Łódź, then I should choose a different subject. So this is a different subject. I would like to talk about models of self-gravitating disks around black holes. We are working on such models in Krakow for quite a time right now. And I listed basically all collaborators who have recently contributed to this series of works. But the subject for today today's talk, and those results were mainly obtained with Wojciech Dyba, Wojciech Kulczycki, and Mikołaj Pietrzyński. So let me see if it works. Not really. Okay. Oh my God.
You need, may I?
Yes, please. Okay, so maybe I do this from the machine, okay?
Yeah, okay. Let's...
No, it's
it's not working now. Okay, now it's working.
Okay. Okay. So perhaps I should start with the motivation. So the motivation is basically twofold. There is an astrophysical context where we could think about where relatively heavy accretion disks or relatively heavy thick tori around black holes. And those situations include cases like, well, a merger of binary neutron stars, for instance, or a black hole and neutron star merger. And then there is this transient short phase where a black hole forms, and this black hole can be surrounded by a relatively massive disk. So, well, with a mass constituting a significant portion of the mass of the black hole. Or the same situation can happen in a gravitational collapse of a supermassive rotating star. But there is also a theoretical context, and today I will be mostly focusing on this theoretical context. And this is that basically the solutions of the Einstein equations that represent self-gravitating tori around black holes, they provide realistic examples of non-vacuum black hole spacetimes, and of course it's always nice to have such examples and see what curious things can happen in such models. Now, also I should mention that numerical simulations of binary neutron star mergers, for instance, suggest that the disks that form in such events, they basically obey the Keplerian rotation law. Whatever that means, I will try to make clear later. But I will focus on this Keplerian case in the remaining part of this talk entirely. So, well, let me start with saying that the formalism that we use is mostly based on a work by Masaru Shibata from 2007. And of course, this has been upgraded in order to include magnetic fields right now and rewritten by us and so on. But but basically the formal setup is coming from this work. And we work as follows. We assume the energy momentum tensor of the ideal general relativistic magneto hydrodynamics. So I will comment on this later, but this is essentially and the energy momentum tensor corresponding to perfect fluid plus the energy momentum tensor of the magnetic electromagnetic field. And this formalism of ideal magneto hydrodynamics, well, first of all, it's very well known, and this is a standard thing that people use in astrophysical simulations. But it's based on a special ansatz and prescription of the magnetic field. It's convenient to use the full vector of the magnetic field. And assume that this full vector is orthogonal to the full vector of the fluid velocity, which is denoted by u mu here.
Question.
Yeah.
What is the velocity of magnetic field? What does it
No, not the velocity of the magnetic field. We've got the fluid velocity. Okay.
Yes, I understand.
Okay. And what we say here is that we construct the vector of the magnetic field. Well, normally magnetic field is described by a free vector, and you put this free vector into a four vector, and you construct a quantity like that, with the condition that it's orthogonal to the full velocity of the fluid.
Yeah,
And
but this form of the energy momentum is very peculiar. The d mu times d mu. In what situation we can?
no, it's not. I wouldn't say. Well, let me comment on this later. Okay, I think it would be more clear. So this condition can be also translated as a condition that says that if you move with a fluid, then everything you see is only magnetic field. Now, the next assumption in construction is that you take a particular form of the dual to the Faraday tensor, and this is precisely this assumption. And in order to say anything more, I have to specify the metric, or at least in order to say something more in this context, I have to specify the metric. And I will be working with, in spherical coordinates, but the metric will be stationary, axially symmetric, and circular. And then I can write it in the following form. So basically, that means that the shift vector has only one azimuthal component here. And the technical assumption here is that all those metric potentials, they depend on r and theta only, so they are independent of the time coordinate and phi. And then, in this case, we've got two Killing vectors, which can be written in standard form. So there is this azimuthal Killing vector and the time Killing vector responsible for stationarity. Now, the configuration that we will talk about is such that we will consider only axially symmetric stationary configurations where both the full velocity of the fluid and this full vector of the magnetic field is allowed they are allowed to only have time components and azimuthal components. So all colloidal components are set to zero by construction or assumption. And we also assume that they only depend on r and theta. So everything is stationary, and it means that you've got no colloidal motions, for instance, when it comes to the motion of the fluid, and that the magnetic field in this configuration is only toroidal. So basically, you've got fluid moving like that, and you've got magnetic field also oriented like that. And this, with a little algebra and normalization conditions, allow you. This allows you to show the following relations between the components of the magnetic field for vector and for velocity. Now,
is omega constant? Omega.
No, it doesn't have to be constant. Omega is this ratio of the components of for velocity, and we will have to specify it later on by some condition that you can impose on this ratio. Now it's not constant, so the disk is assumed to rotate in a differential manner, right? You can rotate faster in the center, slower at larger distances from the.
If you write a electric tensor,
Yes, please.
you also need some conditions for G theta, theta, and G phi.
Well, of course, I will be mobile. I will specialize to. I will specialize to yet another choice later on, compatible with that. But a few formulae can be written already for assuming that little or that much. Yes, of course. Yes, of course. Yes. So yes, of course, you need boundary conditions as well. Yes, of course. Yeah, you're right. So we impose such conditions. Now, let me comment still on this construction of ideal general-relativistic magneto-hydrodynamics. So basically, it means that your energy momentum tensor is simply a sum of the energy momentum of the perfect fluid that is well known, and the contribution, which is a standard contribution from the electromagnetic field, and this is also the standard expression. And what we get, or what we started with, which is this textbook expression, is basically this expression for the energy momentum tensor of the electromagnetic field with this ansatz for F mu.
This is what bothering me, because do we have the electric field or not?
Yes, you do have electric field, because if you've got magnetic fields and that thing is
So somehow expressed by you.
This expression here basically tells you plus a collection of formulae which I could write and I didn't write because they do not constitute this model that we solve eventually. But the situation is that if you put your observer locally so that it moves with the fluid, then what it observes is only the magnetic field.
Yes, this condition.
Okay, and of course you would have electric field if you move in a different way.
Okay, so you produce this field by transformation. Electric field.
Yes. If you want to look at it. Okay. But for instance, it will not appear explicitly in the equation, so I do not need to have this in this construction. And also, for instance, under those symmetry assumptions that are listed here, the homogeneous Maxwell equations are satisfied automatically for this ansatz. Well, you take the Hodge dual of F mu. The point is that if I write that this ansatz looks nicely for f mu, for the dual of the f mu nu, and it doesn't look that nice if I write it explicitly as an expression for f mu nu, which would be perhaps more natural, right? But of course, I can now, you know, put a Levi-Civita tensor here and say and forget about the star and say that this was my answers for f mu nu, but it's much more obscure. Now, in this formalism of magneto hydrodynamics, what people do is, or basically the logic is that the equations that you would solve, they stem from the conservation of the total energy momentum tensor. So you do not specify currents. And if you look to how people do those models, then you will see that almost nobody puts any comment whatsoever about currents. But if you are interested, you can of course compute the currents that appear here. And in this case, and simply because you can assume that you solve the conservation equations, that you get f mu nu, and that you compute the current. And in this case, what we can learn is that there will only be a poloidal current. Okay, so if you want to have only toroidal component, the current, if you compute it mathematically, it's poloidal. Basically, you can also write the general formula for the current as in electrodynamics in this case. So this would be well, the effective current charge density times the for velocity of the fluid plus this expression where sigma is the so-called electric conductivity. And now the ideal general-relativistic magneto-hydrodynamics, this is a limit where you assume that sigma is infinity and this is zero. Okay.
What is the product?
And the product is something that you get from the solution. And this is precisely our case. So we do not have this current, we've got this current, and we can compute it a posteriori if we are interested. So in this the very simple setup, what you can do right now is you can write down the equations that express the fact that the four divergence of the energy momentum tensor vanishes, and this can be reduced to the following algebraic expression, where basically you can distinguish or have three parts, and the first one would include this integral, where J is this kind of product of ut u phi, and well, that there is this term where H is the specific enthalpy of the fluid, well, and is defined by this relation, or related to the pressure and the energy density of matter. Sorry, the resonance density of matter along by this expression. And there will be also a term which is due to the magnetic field component only. So everything that remains from the magnetic contribution is this part B squared, which is essentially well, the square of the magnetic field or magnetic pressure, as it's sometimes called.
This ut times u phi is
No.
function of omega only is assumption.
Okay, so let me put it that way. If you do not have magnetic field, then you can say that the integrability condition for those equations require that this expression, which you could interpret as the specific angular momentum, can only be a function of omega. Okay, so of course it changes from place to place in the space-time, but in such a way that it has to be a function of omega, which can also change. Now, in this case, this is not that obvious. So to make things simpler, we just assume that. Okay. And if we assume that, we first of all keep in touch with standard models with no magnetic field. And then we have to do two things. We have to specify this function in order to specify, generally speaking, rotation of the fluid. And this is precisely how we do this. So this is the answer to the previous question. We specify rotation by saying how this specific angular momentum depends on the angular velocity. And this is a sort of covariant way that's used in such models in GR. And we also have to specify how somehow this term regarding magnetic field. And I will come to this. And we have to specify the equation of state in order to deal with this. Okay, here I just comment that saying that J being this combination, which appears quite naturally here, is the specific angular momentum is not the only possibility. In the literature, you can have other choices. For instance, this looks quite nice as this L is very clearly expressed, in terms of products of the full velocity with killing vectors. And but in this setup, it's related simply to J. So this is also well known for people who are working in this area. Now, when you specify what happens with the system by handling those two terms. And the first difficulty is how to specify the rotation log, this dependence between J and omega, the angular momentum and the angular velocity. And we were fighting with this for quite a time because we wanted to have a prescription that would reduce to Kerr, Keplerian motion in the Kerr spacetime when in the limit when the mass of the disk is negligible. And it turns out that this is the formula that we could derive working for instance, geodesic circular motion on the equatorial plane in the Kerr spacetime. And working generalization of this formula that allow to include self-gravity of the disk is this one. So basically the change you do here is that you replace this mass of the Kerr metric with an arbitrary constant W, which is unspecified a priori. And the idea is that you keep the A parameter, the spin parameter of the Kerr, as a spin parameter of the black hole that you eventually would like to put in the center of your system. Also, the good thing about this is that in the Newtonian limit, one obtains a standard relation, which you would naturally call a Keplerian one.
So this J of omega does not depend on a specific choice of orbits.
What do you mean orbits?
So you have one orbit, one geodesic motion, circular. No.
Well, I have to specify basically some relation, and a priori I have no way of doing it. You could even have an impression that you can specify whatever you wish. Okay? This is not entirely so, because if you do this in a wrong way, you usually will not get solutions to this set of equations eventually. Or what happens rather often, you get solutions, but only in a limited range of parameters. So the quest here is to find a prescription that will produce a solution almost always and have some, justification. And our final,
So are you deriving this last result, or this is just working guess?
This is a result which you derive for test fluid or dust orbits in Kerr-metric at the equatorial plane. This is just a calculation. It can be an easy one or a difficult one, depending on the coordinates you work with. In our case, we are working with some quasi-isotropic coordinates, and this is a difficult task. But well, once you understand how much this is covariant, how much it is not, but this is not time to discuss this right now, then probably you could start with Boyer-Lindquist, and this is easy and transform to the coordinates with which you would like to work eventually. But then the postulate is that the similar form will also work for self-gravitating systems, where of course the metric will no longer be a Kerr metric, and basically what the metric you will get will depend on what you assume about the rotation of the fluid as well, right? Because
So what is M?
so here M is the Kerr mass, and here M is absent. And well, when I comment that it's no longer M, I just mean that it's no longer equal, that W squared, it doesn't have to be equal to the mass of the central black hole.
That is bigger than M?
It is bigger than M, yes. Yes, it is bigger than M and smaller than the total mass.
So does this energy have this matter have so much support?
Yes, we will assume that later on. Yes, yes, we construct.
Okay, so it makes sense to define M. This sphere which surrounds everything.
I can have idea mass at the end if I wish. Yes, yes. Of course. A comma is known to be very wrong in those cases because, at least locally, for instance, for the black hole. So you can have negative comma mass for the black hole. Yes, then it's okay. Then ADM would work, and we use ADM. Okay, so that's what we do. Now there has to be some guess about equations of state. I use polytropic equations of state in this talk, but in other papers we were also working with tabulated, nuclear physics, sophisticated equations of state. You can also do. If you wish. Now the point is to define magnetic field and somehow prescribe this distribution. And there is no hint, or at least I did not have any hint. So this was a situation we know from this integrability condition, which holds right now, that this expression b squared times this modulus of L, which is that this has to be a function of rho times h times this metric, a factor. And then again, you can specify anything, and this is my ansatz. The reason for this ansatz is as follows. Firstly, it guarantees that if the energy density goes to 0 at the edge of my disk, then the magnetic field goes to 0 as well. And also the Euler-Bernoulli equation, this equation, when I put all my ingredients, this has this form, and basically this magnetic part, which enters here, has this power law form, similarly to the expression for the enthalpy, which for polytropes has also a power law. But there is no more physics about why this choice.
Afterwards, you can verify your choice.
Well, I don't think that I can do this right now. Okay. Yeah. Okay. So, in a sense, the only thing this choice does for me is that I've got my my magnetic field, which is trapped in my fluid, and outside the fluid field region, I've got vacuum. Okay, so I don't have to bother with solving Maxwell equations in this vacuum region. Of course, I could do this in a different way, but that's a setup. And now there is well, there are some slides which are pretty complicated, and I'm just I will basically browse through them. So I'm showing them because this is a relativistic community seminar, so everyone wants to see Einstein equations at the end. But this is a standard formulation, or maybe not really standard, but based on standard ingredients. And there are technical assumptions regarding how we take care of boundary conditions, and they are essential, but there's not normal physics that we define at this stage. Okay, so for instance, we can start working with standard ADM 3+1 splitting of the metric, define the normals to the surfaces of constant time, write, say, Einstein constraint equations. We can write. Well, of course, we have to understand what enters into the constraint equation. So the extrinsic curvature has to appear here, and so on. There would be those matter terms that we have to also define. There will be the evolution equation, okay, which also has the very standard 3+1 form. And we have to assume at this stage that we set for a stationary configuration, which amounts to the fact that, you know, the time derivative of the extrinsic curvature would be 0 in this case. And in those coordinates that we work with, time derivative of the induced metric will also be 0. Okay. We have to compute all those terms. And at this stage, specify to a given metric, well, specify something more about the metric, and we use this so-called quasi-isotropic gauge, which basically means that the metric, which is compatible with the previous form, has this form. So, for instance, you could also have curve written in such coordinates if you wish, right? This is not convenient, but it is very convenient numerically for us here when we include matter. And then there is some job which we have to do regarding the shift vector. We split it into a part which will, I'm sorry.
The phase beta is different.
Yes, of course, it should be T. One should be T, sorry, one should be T. So the idea is that we split the shift vector into a part that will be somehow associated with the black hole and the part which will be somehow associated with the torus. And you do this in a way that if the torus is absent, everything that remains is just this part corresponding to black hole, and then you reduce to K. And if the torus is present, then, you know, there is some mixture of those. And all these constructions, all those constructions are required in order to put the black hole in the center. Because you know, putting black hole in the center means that you have to somehow specify boundary conditions that will guarantee you that you've got a horizon, and that you can numerically handle this horizon. And there is a trick known in the yes. Not yet, not the full system. Yes, okay. The standard formulation, yes, this is the starting point. No, no. Right now, I only assume
Just solve it.
stationarity and axial symmetry, and then I will write them explicitly, and then I will have to solve them. Okay. So the big thing here is to put the black hole in a way that you can, at the end, integrate numerically from the black hole, from the horizon outside, and everything behaves nicely. And there is a trick for this, which is called puncture, and this was discussed for, in many papers, essentially for all those techniques where you evolve numerically black holes. And so following Masaru Shibata, we take this formalism and we use it. We find it to be the best working one right now. So basically, this means that we will have some boundary conditions on the horizon, and by construction, we can put we can say that by imposing boundary conditions on a given sphere, on a given coordinate radius, we can make the sphere to be an apparent horizon, and actually a minimal surface at the same time, because the gauge will eventually be the maximum gauge. So this is the system that we have to solve eventually concerning Einstein equations. And this does not look that bad. There are some elliptic equations, but the right-hand side is, of course, the disaster, right? So this is what you do. So of course, I mean, there is no sense that you enter into the details, and then I try to explain that.
This is answer to your question.
Yeah. So basically, you solve that on the computer. So what I didn't discuss right now is how we define the masses. This was also already a question by Professor Lewandowski. How do we define angular momenta, etc.? What I do numerically with asymptotic boundary conditions. So yeah, there is plenty of details that there is still to discuss, perhaps. But let's go to some nice stuff. So we have to somehow parameterize the solutions right now. Okay, so the system is the black hole and this torus of gas. I want to have a torus of gas. It has to be of compact support. And I can parameterize the problem with those parameters. And these are two parameters that I impose as a part of this construction, and they control the black hole. There is a mass parameter for the black hole, but this doesn't have to be exactly a clever answer to the question about the mass of the black hole. So what we do later, we compute the Christodoulou irreducible mass for the black hole mass, but this is controlled with this parameter in a way, which is not clear. So you have to have a numerical solution in order to find a better approximation to the black hole mass in the system. A would be essentially the spin parameter of the black hole. R1 and R2 would be the inner radius of the torus and the outer radius of the torus at the equatorial plane of the disk. But these are coordinate radii. Gamma would be the polytropic exponent. Rho max would be the maximum density within the torus. And N and C1, these are those parameters used to control the amount of magnetic field that we put. And they appeared sorry, here, right, in this prescription, N and C1. Okay. And sometimes I will use this conventional magnetization parameter, which is essentially the ratio of the thermal pressure to the magnetic pressure. And I compute this at the maximum of the density within the torus, and this is supposed to somehow tell you how the fluid is magnetized. So when you take the computer and you learn how to solve those equations, you get solutions. And here we plot meridional cross sections of the density. And this is basically what you get. Now, in those models at the bottom have more magnetic field. Everything else is fixed. So the first lesson that we get is that the more magnetic field we put, the maximum of the density is shifted to the center, more to the center of the black hole. It's just what it is. Also, what you get is that if you take less massive disks, they become thinner. This is also known for, so those are thinner than, say, those. And those disks are just slightly more massive than those. This is actually common to non-magnetized fluids as well, disks that obey Keplerian rotation. This Keplerian rotation has this nice property that, at least numerically, no matter how light the disk we take, then with this expression we can find a solution. But this statement is very sensitive to this choice of the Keplerian prescription. If I change anything in this lengthy formula, then this property will be gone, and you will not be able to build very light disks in this full formalism around the black hole. And this is, well, in a sense, well known. So, for instance, you cannot put such a compact disk which is rigidly rotating on K. So, but the key assumption here is that we search for configurations with compact support.
We rotate it?
Yes, this is rotating. I mean, this is rotating. This is a meridional cross section because, okay, this is R, this is X and Z. R sine theta, R cosine theta. And the density is color coded. Oh, actually, it's we scale, of course, appropriately. So, because of equatorial symmetry, which we also assume, sorry, I didn't mention that, you have to understand that there is a disk here as a part of a disk as well. There is a black hole here, and there will be a cross section here, and then you have to rotate. Okay, that's disks. This is again a picture that tells you that if you put more magnetic field, then this maximum of the density goes towards inner regions of the disk. This could have astrophysical consequences. I'm not going to do fast.
Okay, so this doesn't approach the black hole. There is a distance between.
Yes. Yes, because I do not want to have any info into that black hole. Just a perfectly stationary solution. I cannot put it in the black hole. This is forbidden. But I can touch the ergosphere, and I will show how this looks. What else can be observed here is that if I try to increase the magnetic field, what happens is that the gradient of the magnetic pressure takes the role of the gradient of the thermal pressure in counterbalancing gravity. So basically, these are weakly magnetized disks. These are highly magnetized disks, and the dashed line corresponds to the thermal pressure, and the blue one is the magnetic pressure. So basically, what happens when I put more magnetic field is that it's magnetic field that starts to be responsible for the equilibrium. But in all cases, all those pressures, relativistically, they are of the order of at most 1% of the rest mass density, or the energy density. So basically, the magnetic field itself is not the main contributor to gravity. It changes very much dynamically the structure, but it doesn't weight, so to speak, more than 1%. But what happens if I take massive disks right now is that there is a non-uniqueness of solutions. So basically, what happens is we start observing standard nonlinear phenomena known in such nonlinear free boundary systems. And there is a very, very strange and I think quite elegant bifurcation occurring here. So what happens literally is that if I specify those parameters that locally fix the solution for me, I can usually observe two solutions.
What is missing? C1 or something?
Oh, sorry, C1 and I'm sorry, thank you very much. I should put C1 and M here. But I think I will start with example. Okay, so I will now start with examples with no magnetic field, just for start, because the effect that I'm going to talk about right now holds also true for purely hydrodynamical configurations with no magnetic field. So actually nothing is missing, but I should have said right now that well, this effect appears for magnetic fields as well. I will show an example as well, but I will, for simplicity, let me start with pure hydrodynamical configuration with no magnetic field. And still, I've got this set of parameters, and locally it specifies a solution, and I understand that globally, usually at least two exist. And what I can draw are those pictures where I set all the parameters, and here I draw the maximum restless energy within the fluid, within the torus. And in order to draw some picture, what I plot here is the ADM mass of the total configuration. And the black hole mass parameter is around 1. So here, for simplicity, also this is a non-rotating black hole with spin 0. Then the true mass, or say, Christodoulou mass of this black hole is different than 1, but it's roughly of the same order. So here, of course, I went extreme. I allowed for extremely heavy disks of masses of orders of hundreds of the black hole mass. But the picture is then well visible. Well, I've got this branch of relatively light disks, and I've got this branch of very heavy disks. Well, for a given rho max, well, there are usually two solutions, one here and one here. And above a certain threshold, there is no solution. And so it turns out that I cannot specify this rho max as I wish. But it turns out that the huge masses can be obtained also with relatively very small energies, small energy density. Now, this is not an effect of
so for very small densities, you have 2 or 3 solutions.
Here, no, well, I have one solution here and one solution here, and these are two different gammas, two different equations of state. Okay, just to illustrate that this does not depend on, other details of the model, that this is a general picture. One thing that you might be worried about is that perhaps, those radii are simply coordinate radii. So these are, coordinate radii, coordinate radius in a metric that you get somehow as a solution can be anything. So maybe you should do better. And the way to do this better was to take, instead of coordinate radii, the so-called circumferential radii. And I will define this later. Circumferential radius is basically the circumference of the circle divided by 2 pi. And this is a geometric quantity. And the same picture remains. So here we've got the models where we fix those circumferential radii of the inner part of the torus and the outer part of the torus, and basically the same kind of graph can be obtained also numerically. Here, of course, every dot is a given separate solution. So now the question is how to understand that. But before I tell you how to understand that, let me comment a little bit more on the circumferential radius, because this is also something that comes into play here. So as mentioned already, this is the for a given circle, this is the circumference divided by 2 pi. So in our metric setup, this is basically psi squared times r times sine theta, when this is a circle of constant radius and constant theta. And you can also have this expressed covariantly in terms of Killing vectors. This is well known. And well, it is actually known, it was known already by Andrew Petrov and Lagrange in 2007, that in such systems, the circumferential radius doesn't have to be monotonic with the coordinate radius. So what happens is that if you plot the circumferential radius against the coordinate radius, if the disk is massive enough, and here the range occupied by the disk is gray shaded, then the circumferential radius can have a local maximum. So basically, the circle with the largest circumference that you can embed in such a torus is not the outermost one at the boundary, but a circle somewhere in the middle. And this somehow comes into play here. So let me say how we understand this and why this is I think quite curious. So what we are, the situation that we are dealing with is as follows. You've got tori, which when you look at them from outside, they basically look similarly. So for instance, in geometrical terms, they have same inner radius and same outer radius. Also in this cross section, here then they are flattened, but if you take those massive solutions, they are actually quite circular. Okay. Because with mass they grow more thick, and at the end they are more or less circular. So you've got something that from outside would simply look like a standard geometrical torus, and you fix the radius. And you fix the maximum density within the torus, and yet you get completely different masses. So this has to be understood in a way that simply one torus has a completely different volume than another one. Although they have surfaces which geometrically are characterized by, well, sort of or more or less the same. And so there is an example of how we try to visualize that. And this is, of course, a naive way. So a naive way would be to estimate the Euclidean volume occupied by a torus. Is what you would do. You could take a Euclidean formula. This is known as Pappus-Guldinus rule. It's an ancient formula known already to Pappus of Alexandria, which you apply to a torus, and here R1 and R2 and are basically the inner and the outer radius of the torus. And here you assume that it's a torus, that you rotate a circle around an axis in order to get a torus. And you could try to contrast that with the actual volume. I mean, the word proper is wrong here. with the geometric volume occupied by a torus on a given time slice. And you could try to compare this, and this is plotted in the logarithmic scale. And the Euclidean volumes for some given families of models are plotted here. And the true geometric volumes are plotted with those dots. So what you see is that you, and this is against an ADN here, or against that's the outer circumferential radius here. So what you see is that if the disk is large, then this volume is, well, if the disk is less massive, then this volume is less than what you would expect. But then those disks could be even, quite, well, not so much big. But then for massive disks, it's simply, the true volume simply exceeds, much exceeds this expectation or Euclidean expectation. So this torus, in the sense of volume, is much larger than you would guess, okay? And hence you can understand that there is this bifurcation of theory. Okay, I have to speed up, so let me comment for those who would inevitably ask this question. We believe that those massive configurations are unstable. I mean, we were not doing any numerical simulations on that, but at least for non-magnetized cases, there is a condition due to Seguin, which gives you a necessary condition for linear stability against axially symmetric perturbations, and it can be rewritten in our case, and we can check. And more or less, you could say that the disks on those massive branch stop fulfilling this Seguin stability condition, and that those do. Okay, so this is again, a confirmation that perhaps everything is okay. Okay, another thing that can happen is that you could have quite intricate structures when it comes to looking for ergospheres or ergo regions. So in this setup, the ergo region is defined as a region, well, outside the black hole horizon, where the killing vector, the one which is asymptotically time-like, becomes space-like. So basically, this condition has to be fulfilled. And if we search for such regions and we allow for massive disks, then what we get is as follows. We've got, of course, ergo regions around black holes, as we would have them in the Kerr case. But what can happen is that we also can have such ergo regions within tori. If the torus is sufficiently massive, you can have cases where the entire torus is within the ergo region. And you can have also the case where the two ergo regions, the one associated with the black hole and the one associated with the torus, merge. Okay, and the topology changes. I think this possibility, well, first of all, again, for rigidly rotating tori, this was observed by Andrzej and Petrov, and then Piotr Hruszczo, with collaborators, they had a paper on the regularity of this possible intersection at the moment when they start merging. So there is some science you can do on that. How much time do you have? I feel I have to finish, but
up to say 10 minutes.
Okay, thank you. So what I would like to finish with is something newer. Namely, I would like to now comment on what happens in all those curious structures when you include magnetic fields. So for instance, what we know right now is that on those bifurcation plots, the mechanism and this bifurcation and non-uniqueness of solutions is preserved. And here we plot solutions which are more and more magnetized. And they all go, well, this is the no magnetic field solution, and here we increase magnetic. And in order to understand that this is the increase of magnetic field, we plot this magnetization parameter here. But you can forget about looking at that, and believe me that those solutions here have more magnetic field than those here. Okay? So one immediate consequence is that this maximum allowed density within the torus seems to be lowered by the introduction of the magnet. But what you can also see on this plot, but I have to comment on this, is that some of those branches are not continued to the light as light branches. And this is because we simply cannot find solutions here. This doesn't mean that they do not exist, but I would guess so if you ask me. And the reason is that, you know, this Keplerian prescription is actually very special. It is very special if the disk is, you know, has no mass. It reduces to this disk of dust on the curved spacetime, on the equatorial plane. So the disk becomes thin and light. You can have this limit. But I was talking or mentioning already that this property is very sensitive to the details of say, how you prescribe the rotation law. So what we do here is we keep this prescription of the rotation law, but in the same equation, we put some magnetic field in a way that is not adjusted anyhow to this property and to the structure. And simply, what I understand about this is that that we put too much magnetic field, and this configuration loses this Keplerian property, and you simply, with too much magnetic field, which was not somehow adjusted, you just cannot produce very light disks. And of course, if you put a lot of disks, magnetic field, the only way to handle this is to go to high masses, and then you know you change the metric accordingly considerably. It's no longer curved at all. Now, unfortunately, this very simple reasoning that all those curves go down with increasing magnetic field is not true. You could also find examples where the inner radius is closer to the black hole, where the situation is reversed. And so this is an example showing you that not everything is that simple here, unfortunately. But what can we say about, say, this behavior with the circumferential radius? We try to check pairs of solutions that have same asymptotic ADM mass, but differ with, and the same parameters, but differ with magnetization. We do not want to have the same maximum density, just the same total mass of the system, or total mass of the torus. And it turns out that, for instance, this property, this non-monotonicity of the circumferential radius, this practically does not depend on the fact that you have put magnetic field. Okay? Those pairs, these are plots for a magnetic field magnetic configuration and purely hydrodynamical configuration. And also, if we look at ergo regions for those very massive disks that produce their own ergo regions, so to speak, then we see that, well, this is also not affected. So the top is with no magnetic field, the bottom is with magnetic field, all the other way around. No, the lower panel is with no magnetic field. These are isocontours or isolines of density. So this is changed, but the ergosphere is basically at the same place. So and we can, you know, you can repeat this with other examples as here. So the picture would be as follows, that when it comes to those effects and the magnetic field in those configurations, you can put a lot of magnetic field. This bifurcation pattern is preserved. It changes because you talk about actual energy density. I mean, the way you plot those diagrams. But when it comes to those characteristics of the metric, not surprisingly, they do not depend on the small contribution of the magnetic field. They depend on the rest mass density distribution. So this magnetic field changes how the structure of the disk. This disk then affects the space-time, right? And if you choose two different configurations with the magnetic field that basically have the same mass and the disk is more or less similar with respect to the density distribution, then the space-time is basically the same. So nothing changes here. So basically, this geometric lesson can be knowledge can be inferred from purely hydrodynamical models. Okay, so this is last slide, and let me say what I did not discuss here. So I didn't discuss the relations between mass sizes and angular momentum. This was done, and then you can test various inequalities. I didn't discuss possible generalizations of this Keplerian law. This was also done. I didn't discuss models with realistic equations of state. Well, definitely what remains to be done is this check for numerical stability, or rather instability, and what really happens, how this evolves. And probably, if one is interested in generalizing such models to include poloidal magnetic fields, and probably both toroidal and poloidal. So there is some outlook for this research, but thank you very much. Yes.
Astrophysically, how is it really so that this magnetic field around black hole is completely supported within a tori, or
No. This is approximation. But when you look for, say, more some models which are well, you do simulations, right? So you are not trying to do this analysis, but you put some data, do a simulation. Then what happens is that very important phenomena depend on this part, which on this magnetic field, which can be weak, but it's outside.
Mm-hmm.
So, for instance, everything associated with the formation of the jets. Those things happen in the region where you've got no disk. Okay. So, for instance, there is a numerical work on binary neutron star mergers, and they have this kind like that, and they start from completely independent on this with respect to this, completely arbitrary configuration at the beginning. So you start with neutron stars with, say, poloidal magnetic field. You evolve this, you've got the merger, you've got the black hole, the disk forms. And I was quite surprised to find that the magnetic field in those simulations, of course, it's not perfectly stationary, and of course, everything you know is what you see at the plots, is that it's more or less toroidal. It's more or less captured by the disk, but there is this completely non-toroidal, but rather poloidal contribution outside the disk. And then it's responsible for the jet. Okay, so of course, depending on what you look at, those two regimes can be very important.
I have a question, please.
Yes.
Can you hear me?
Yes, I do hear you.
Okay. Rotating black holes with accretion disks have usually jets as well.
Yes, that's right.
Is the theory of the formation of jets related to the formation of disks, or it's completely different?
Well, I would say that the numerical knowledge on that is that you can form a jet in a numerical simulation, magneto-hydrodynamical numerical simulation. And so you can start with at least you can do this on Kerr, and then perhaps it's best visible. You start with some angular momentum at disk forms and also at jet forms. Yeah, so then this is those jets can be modeled as within magnetohydrodynamics. But this is probably not the end of the story. This is my understanding, that there is more to jets than just magnetohydrodynamics. Mm-hmm. So
thank you.
This is by construction, of course, neglected here.
Okay, thanks.
One question?
Yes, what is the global structure more or less of space-time? So there is horizon,
Yes.
and now horizon is surrounded by vacuum space-time, or
The horizon is locally surrounded by vacuum. Then there is this disk with density of constant support of compact support, and then by construction, the asymptotics is more or less of Kerr.
okay. And now, if the magnetic field is present,
Just more or less.
is horizon still vacuum, or it is in some?
It's still vacuum because we have those conditions that in those models we've got those conditions that that the magnetic field is frozen or kept within this configuration.
Okay.
By construction, if you do this differently, then you would have to impose boundary conditions for the magnetic field at the horizon.
So magnetic field is not present.
No.
No,
This is a simple model. No.
Okay, and now this space-time in neighborhood of horizon.
Yeah.
Is it an exact solution, or is
It's a numerical solution.
it?
Yes.
I see. Can we measure departure from Kerr?
Yes.
Okay, so this is Kerr, so I can think of this as before Kerr. but
Yes.
this is not
Yes.
linear
Yes.
theory of distribution before.
Well, I was not analyzing that much how the details of how much this departures from Kerr, but it clearly departures from Kerr. So
And-
we were looking at that at some
and
stage,
and it's
plotting
not
some
anymore
functions.
the Petro-
Sorry?
And the right answer is not anymore of the Petro-
Oh no.
Other questions? Thank you again.
Yep. Thank you.